Hello everybody, we're welcome back to the section with calculus. Today we'll be talking about the derivative of log functions. So prior to this, we talked about the chain rule, we talked about the product rule, quotient rule, and also implicit differentiation. So please note that if you are missing any of this stuff, make sure you go back and look at some of the stuff that I posted, or if not, look at a textbook. So today we're going to be talking about how to find the derivative of the following log functions. So you can see right there, what is the derivative of natural log of x, or what is the derivative of log base a of x, and also finally what is the derivative of natural log of absolute value of x. So we're going to be proving those up there, and also in addition to that, we're going to be proving some of these I guess limits that we kind of took for granted for back in the very beginning of calculus when we tried to prove the limit but we couldn't, so we used a calculator. So this time around we can actually prove these limits using I guess what we learned right here. So let's go ahead and begin by proving the derivative of natural log. And if you looked at my last video in implicit differentiation, I actually did prove that the derivative of ln of x is supposed to be 1 over x using implicit differentiation. I guess we can go ahead and do it again, but this time I'm going to go ahead and use a variation that you would probably see that's going to be a little bit more formal in the textbook then. So here we go. Taking my first one, I am going to, give me 1 second. I need to charge or synchronize my pen, and hopefully that'll work out. Sorry, it looks like it's going to be a small little slight technical difficulty here. Hopefully this will work. And there we go. Okay, sorry about that. So let's see. Let's go ahead and prove that on the side. So the derivative of ln of x. So here is what we normally see in textbooks. We have y will be equal to ln of x. And what we'll do is, since we don't know how to take the derivative of ln of x, we're going to go ahead and move it to the other side then, giving us the following. E to the y is equal to x. And what that allows us to do is allows us to take the derivative using implicit differentiation. So taking out what I have right there, if I use implicit differentiation, take the derivative of both sides. The derivative of x on the right-hand side is just plain old 1, whereas the derivative of e to the y on the left-hand side, according to implicit differentiation, we first have e to the y because e to anything, the derivative is always just itself. But because y is a function of x, and according to implicit differentiation, that's where we're going to get an extra y prime, or dy dx, according to the chain rule. So focus on the y prime because that's what I would like to solve for. I am going to isolate the y prime. So y prime is now equal to 1 over e to the y. And normally we would say, okay, it's done because we've isolated y prime all by itself. But if you notice in the second step over here, e to the y is equal to x. So we can actually make a substitution. And in fact, we want to actually do that because if you remember also, if we start with an equation where it's y is strictly equal to a function of x, I would like to end with y prime is also a function of x strictly. So finally, making a substitution, we get y prime is equal to 1 over x. And right there, that is going to be our derivative then. Now, going to the second part, I want to take the derivative of not natural log, but the log base a of x then. So in the same manner, what I'm going to do is I'm going to go ahead and say y is equal to the log base a of x. And just like the previous problem, what I want to do, or previous derivation, we're going to go ahead and move the log base a to the other side because I don't know how to take the derivative as is. So if we move it over, this is going to say now a to the y is equal to x. And now we can go ahead and take the derivative using implicit differentiation. So on the right-hand side, the derivative of x, once again, is 1. The derivative of any number to the y power, where a is supposed to be a number that is, I guess, positive in this case, is supposed to be, again, itself, a to the y. But the tricky part now is that, remember, there is also multiplied by the ln of a because just to kind of write on the side, if I have y is equal to a to the x, y prime is supposed to be a to the x multiplied by the ln of a. So that's basically what I'm using as a rule for the derivative. And then in addition to that, we also have y prime because of the chain rule via implicit differentiation. So just like before, we're going to go ahead and isolate y prime. So we're going to move everything that's not y prime to the right-hand side. So y prime is now equal to 1 divided by a to the y multiplied by ln of a. And just like before, we're going to go ahead and replace a to the y with I have in the second step x. So that means my final answer is 1 over x multiplied by the ln of a. So just to give a numerical example, just so you can see how this works out, let's say we have y is equal to log base 5 of x then. Then according to my derivation over there, then y prime is going to be just strictly 1 over x, just like ln of x. But the only difference now is that because of the log base 5, we multiply by ln of 5 in the denominator. Finally, let's look at the last derivation over here, the derivative of ln of absolute value of x. Now, in order to take the derivative of this absolute value, I think we're going to have to break this up into a piecewise function so we can see what's happening in each respective domain. Here's how I'm looking at it then. Ln of x, I am going to break it into two parts. We have ln of x, if it's just by itself, that is for x that's greater than 0. And then we have ln of negative x for x that is less than 0. And for x that's equal to 0, well, we can't take the natural log of 0, so that one is going to be not in the domain. So in each respective function, we're going to go ahead and take the derivative then. So if I take the derivative, then the derivative of ln of absolute value of x, absolute value over here, the upper part where x is supposed to be less than 0, my derivative of ln of negative x, that is supposed to be 1 over negative x according to our derivation. And because there's an inner function of negative x, then that means the chain rule kicks in. So that means I need to multiply by negative 1. Whereas for x that is greater than 0, if I take the derivative, it's just going to be 1 over x. And so the top part, what we're going to get then is that if we clean it up, it's just simply 1 over x. So this is the part that's a little strange because according to what we just derived or we concluded, the derivative of ln of absolute value of x is the same thing as just the derivative of ln of x. And this seems kind of trivial for the most part, but it will actually come into play or it becomes very handy when we get into, I guess, the later chapter on. So for the time being, here's the derivation if you need to come back to it. But we'll see this more in the future when we look at the antiderivative then, okay? Okay, so those are derivation of the natural log derivative. And now let's go ahead and derive what we said last time, which is going to be proving the following limits over here then. So the first one, what I want to do is I want to prove that the limit as x approaches towards 0 for 1 plus x raised to the power of 1 over x is supposed to be equal to e. So the way we're going to prove this, we're going to have to use the formal definition of derivative, and we're going to have to do a little bit of manipulation to show you how that actually works. So let's go ahead and do the following then. So as of right now, let's go ahead and make the following claim then. If f of x is equal to ln of x, then the derivative would then be equal to 1 over x. That much we can claim because we just did the derivation for that. So hopefully that part is okay with you. Okay. Now what I want to do is I want to look at specifically the derivative at x equals to 1 for this function f of x. Now if I want to solve for the derivative, we have two ways of looking at it. One is to go by what we just derived and to make a direct substitution then. So the derivative of f of x is equal to ln of x is supposed to be 1 over x. And f prime of 1 would then be equal to 1. So that's just using what we just derived. But another way of looking at this is by using the formal definition of derivative. So here's what I mean by that then. Okay, we also have f prime of 1 is equal to the limit as h approaches towards 0 of f of 1 plus h minus f of 1 all divided by h. And hopefully you remember that from a very, very long time ago. Seems like, maybe it was like 20,000 years, but, hopefully you can still kind of remember this. So what I'll do is I'm going to go ahead and use this formal definition and make our substitution then. So let's see, the limit as h approaches towards 0, f of 1 plus h, that is going to be ln of 1 plus h, and then minus f of 1, that is going to be ln of 1. And again, all of that is going to be divided by h. Now keep in mind on the left-hand side, this is supposed to be the derivative at x equals to 1. we actually know that value because remember, we just said that the derivative according to what we just derived is supposed to be equal to 1. So that is supposed to be equal to 1 then. Now, you know what you're thinking, where is this going to lead into? So you're just going to have to bear with me and then you're going to see what's going to happen in just a little bit, okay? Okay, so let's go ahead and carry on. The ln of 1, that is supposed to be equal to 0, so that's the easy part. So let's just go ahead and erase that part. Now, let's go ahead and rewrite this now as the following. 1 is equal to the limit as h approaches towards 0 of 1 over h multiplied by ln of 1 plus h. So what I did was I just rewrote this fraction, the fraction as a in a different form. So then that way you can see it as a multiplying function or a function that's multiplied. And the reason why I wrote it this way is so that you can use the property of ln to bring in that 1 over h then as an exponent. So what I'm saying now is let's go ahead and take that and bring it inside. This is going to now say the limit as h approaches towards 0. And we're going to go ahead and bring that inside as a multiplier. So it's good. Oh, sorry, not as a multiplier, but as an exponent. So the limit as h approaches towards 0 of ln of 1 plus h raised to the power of 1 over h then. Okay. So hopefully you guys are following me so far. And if you take a look at what we have, which is this guy right here, and if you take a look at what we want, which is very, very close, actually, if you notice, because we built most of it. Now, the only thing is we need to get rid of that ln that's on the right-hand side. And the best way for me to do that is actually to take e to both sides then. So if I take e to both sides, you're going to get now e to the 1, which becomes this, is equal to the limit as h approaches towards 0 of e to the ln. Now, those two guys right there, those are going to cancel out, and that's exactly what I'm looking for. So with those two canceling each other out, now that gives me the limit that I'm looking for, which is as h approaches towards 0 of 1 plus h raised to the 1 over h, and that is now equal to e because e to the 1 is equal to e. So there you go. That's going to be our derivation of it then. Okay. And the last one, which is this guy right here, well, that's actually just one step further than from what we have right here. Okay. So here's what I want you to notice. The next thing that I want to prove is this guy right here. E is equal to limit as h approaches towards 0, of infinity of 1 plus 1 over h raised to the power of h. Actually, let me write it this way because I think this way you guys can probably see what's going to be the step, what will be the step that's necessary. Instead of saying h, let me do this. Let me go ahead and replace my variable so that it's going to be like, say, x then, okay? So what I want to do right now is I want to prove that e is equal to the limit as x is approaching towards infinity of 1 plus 1 over x raised to the x power, okay? So basically, just going back over here, instead of saying n, I'm going to go ahead and say x then. So same idea. Looking at what we just proved earlier and looking at what we want to prove right here, you only have to take one small step, okay? And that one small step is let h equal to, or let 1 over h equal to x. And if you do so, you'll see that the first thing that we proved is now the second thing that we're going to be proving. H is normally going towards 0, so that means for x, that is going towards infinity. And also, all the h is going to get replaced with 1 over x, and also 1 over h is going to get replaced with x. And so there's your derivation then. Okay. All right, so let's now look at some examples that you might see in the textbook as to how to actually utilize the derivative of natural log then, okay? So I usually try to pick 3 examples if possible. One easy one just to kind of get things started, and then the other 2 are going to be something of a medium difficulty and then a harder difficulty. But nonetheless, these are the things that you would see in most standard textbooks. So here we go. Here's the first example. Find the derivative of each example. And the first one, I have y is equal to sine of x multiplied by log base 5 of x squared plus 1. So I'm hoping that you guys can kind of see some of the steps ahead of time right now, that what I need to do in terms of taking a derivative is I need to know the derivative of log base 5, which we do. And we also need to know how to use the product rule, which we also do, because you'll notice that we have 2 functions right here. So if you want, we can go ahead and call this one f, we can go ahead and call this one g, and write it on the side so then that way you can see what's happening then. So here is f, which is supposed to be sine of x. So f prime will be then cosine of x. And if we have g, it's supposed to be the log base 5 of x squared plus 1. Then g prime, according to what we just derived, is supposed to be 1 over x squared plus 1 multiplied by ln of 5, because we're using the derivative of log base a. And remember that there is an inner function of x squared plus 1. So that means that there is a chain rule that we multiply by 2x then, because that's the derivative of x squared plus 1. So there it is. I've set up the things that we need for the product rule. And if you remember the product rule, right, y prime is supposed to be the following. We just basically cross multiply and we add. So it's going to be f multiplied by g prime plus g multiplied by f prime. And if you need to write it out this way, totally fine. But if you can kind of see it or visually visualize all of this in your head, hey, that's even better. So let's go ahead and write it. So f is supposed to be sine of x multiplied by g prime, which I'm going to go ahead and write in. So it's going to be 2x divided by x squared plus 1 multiplied by the ln of 5, and then plus g, which is supposed to be log base 5 of x squared plus 1, and then multiply that by the derivative of f, which is going to be cosine of x. And for something like this, that is my derivative. I'm not going to simplify it because we don't really need to then. So we'll just go ahead and leave it like that then, okay? All right, so that's the easy problem. Now, the second one right here, you'll notice that it is a little bit lengthier, but it's actually not too bad because there's a common trick that they want you to use for the derivative of natural log to make things a lot easier. So here, if I were to take the derivative as is, it's going to be pretty messy because you can see the chain rule, you can see the product rule, you can see the quotient rule, and it's just going to mess everything up. But if you recognize that that natural log, we can use its properties to help us out a little bit. And here's what I mean. First off, notice the numerator, we can kind of rewrite that because, yes, even though we have two factors, that doesn't necessarily mean we actually have to use the product rule. Why don't we multiply everything out? The inside, we're going to have the following. The numerator, if we multiply everything out, that is actually the difference of cube, if you guys remember, or if you guys just multiply it out just to see it for yourself, you're supposed to have a cubed minus 27. Now, unfortunately, the bottom is just going to be sine of a, and I can't do much about that one. And the exponent, now that's going to be the raised to the power of 1/2. And what I want to do is I want to take this and rewrite it in a form so then that way we can easily take its derivative. Because as is right now, it's going to be too difficult. So let's go ahead and use more of the properties of natural log. And again, I have not taken a derivative of any of this just yet. Here's what we have then. The 1/2 we can take on the outside. We have the natural log of a cubed minus 27 divided by sine of a. Whenever we have an exponent in the ln, we can go ahead and take it on the outside. So that's what we did. In addition, the ln of what we have right there, that's a fraction. So we can use the division property for the logarithm. So this is now going to give us 1/2 multiplied by the ln of a cubed minus 27, that's one part, minus ln of sine of a for the other part. And as you can see, now that's actually a lot easier to take the derivative of. So let's go ahead and clean it up one more time. Multiply the 1/2 to everything. So y is equal to 1/2 ln of a cubed minus 27 minus 1/2 ln of sine of a. And here you now don't have to worry about all of those extra chain rules that you would at the beginning. So finally, y prime is equal to 1/2 because the 1/2 carries over, the constant rule. The natural log of a cubed minus 27, well, that is going to be a cubed minus 27 in the denominator, right? So that's the derivative of ln. And then because you have an inner function, we multiply by that inner function's derivative. So that's 3a squared. Then we have minus 1/2 times the derivative of the second part, the derivative of ln of sine of a. That's 1 over the sine of a. And multiplied by the derivative of sine of a, well, that's going to be cosine of a then. So right there, that is going to be our answer. And again, we're not going to mess with this because we took the derivative. So we don't want to fix what's not broken. So here's the last problem right here. And this one, again, this is going to be, it looks kind of very, very easy, but in a way, it's not actually that easy. Well, in a way it is actually. So it's just a small little trick that you have to kind of know. And then afterwards, hey, it'll be very easy for you. So here I want to take the derivative of y is equal to x to the power of tangent of x. And unfortunately, we cannot use the power rule in this case because we don't have an exponent that is a constant. And we cannot use the natural log rule because, well, we have a base that's also not constant. So then that means that we're going to have to kind of play around with this a little bit. So the trick is, well, it's the same as number 2, the one example that we had previously. We want to use the properties of logarithm in order to help us out before we actually take the derivative. So if at any time you're stuck and you see a whole bunch of exponents where the base is a function and the exponent is a function, the best thing to do is actually just take the ln of both sides. So that's where we're going to start. So natural log of y is equal to the natural log of x raised to the power of tangent of x. And as soon as you write the natural log on both sides, then it becomes a little bit more clear as to what you need to actually do then. First, we're going to go ahead and take that tangent of x and we're going to multiply it by ln of x using the properties of natural log. So we're going to take it outside as tangent of x, and then now we're going to multiply by ln of x, all while the left-hand side is still the same thing. So this now is a little bit nicer looking because this happens next. The derivative of ln of y is supposed to be 1 over y multiplied by y prime is equal to the right-hand side. We're using the product rule. So this time I'm not going to write the f and g part. Hopefully you guys can kind of follow. So the right-hand side is going to be the ln of x multiplied by the secant squared of x, and then plus the tangent of x multiplied by 1 over x. Okay, so hopefully you guys can follow that part, not a problem. Focus, I want to get y prime all by itself, so that means I need to move the y over to the other side. So y prime is equal to y multiplied by ln of x multiplied by the secant squared of x, and I'm just going to write it within the parentheses so that way we don't get some terms mixed up, plus 1 over x times the tangent of x. Now again, we did technically solve for the derivative, but remember our rule, right? The cardinal rule is that if you start as a function, if you start with a function of y, if you start with y as a function of x, you need to end with y prime as a function of x. So what that means is we need to replace that y. So my final replacement is y gets replaced back with the original function right there. So this is our final answer. Y prime is equal to x raised to the power of tangent of x multiplied by, well, what we have right here that we see, ln of x times the secant squared of x plus 1 over x multiplied by the tangent of x. And that right there is the part that's a little bit tricky, but hopefully you can kind of understand where all this is coming from. You'll note that because this is still an exponential function in a sense, that's why the derivative contains the original function, x raised to the power of tangent of x. But then all that extra part right there, well, that was all because of all the extra stuff that you have to do. All right, well, there you go. Thank you so much for watching, and I'll see you guys next time. Have a good one.